Today we're going to be taking a look at IMO 2019 Problem 1, which is a great functional equations problem to start with, considering how it's relatively recent and also of quite an introductory level, not using many too advanced techniques or concepts. So the equation we are working with is f of 2a plus 2f of b is equal to f of a plus b. And like with any other functional equation problem, the first thing we should do is try to guess the answer. So pause the video and try to take on that challenge yourself first. If you've given it some thought, you should find that there are two classes of solution, f of x equals 0 and f of x equals f of x equals 2x plus d, where d is a constant. So we can check that these two solutions indeed work, and the remaining work is just to show that these are the only solutions. So after you've guessed the answer in a functional equation problem, the next thing you should try to do would be to plug in some values. And specifically, 0 is really helpful most of the time since it can cancel a lot of things out. For example, if we plug in a equals 0, then we get that f of a plus 2f of b is equal to f of a. And we can also do b equals 0, and we would get f of 2a plus 2f of 0 is equal to f of b. And if we notice, we have these double nested terms on both sides. So one idea is we can definitely try to plug this or substitute this for the f of a plus b there. That might be pretty helpful. So let's take a look. F of a plus b, if we plug it in, let's say the first one, we would get that would be equal to f of 0 plus 2f of a plus b. And the left-hand side would still stay the same, so we have f of a, 2a plus 2f of b is equal to 2f of a plus b plus f of 0. So that's already a much neater expression than this without the double nested. But we still have this 2 inside the function, which is quite unpleasant to deal with. But luckily, if we take a look at these two, they're essentially the same thing. We can just swap out the variables. So we can actually equate these two left-hand sides, and we would get that f of 0 plus, to avoid confusion, let's use a common variable x. F of 0 plus 2f of x is equal to f of x, which, by the second equation, is also equal to f of 2x plus 2f of 0. So the f of 0's cancel out, and we are left with a relationship between f of 2x and f of x. So that's pretty nice. And we can actually just put that in here. Let's move this f of x 0 to the other side, and we would get this. So f of 2a is equal to 2f of a minus f of 0. But we can actually move this over here. So we get 2f of 0 over here. And this is actually a really nice expression if we cancel out the 2's. And it's so nice that I'm going to rewrite it down here. We get f of a plus f of b is equal to f of a plus b plus f of 0. So some of you that are more familiar with functional equations might recognize that this looks really similar to Cauchy's functional equation, which is this. So with Cauchy's functional equation, if the domain and codomain are rational numbers or integers equivalently, then we have that the only solution to this equation is f of x equals cx. But the problem is we actually have quite a troublesome f of 0 term on the right hand side, so that is a bit annoying, and we want to get rid of this constant. So how can we actually do that? Well, we can use a substitution here. Let's say we have f of x is equal to g of x plus f of 0. So we're defining a new function g, and we're defining it as g of x equals f of x minus f of 0. So let's substitute substitute the f's for g. So we get that f of a is equal to g of a plus f of 0, and f of b is equal to g of b plus f of 0. On the right hand side, we have f of a plus b is equal to g of a plus b plus f of 0, and then we also have the last f of 0 here. So what's nice with this substitution is that since we only had one function term on this side and two on this side, they would generate two f of 0s, and this would only generate one, but it already has an f of 0. So there's actually two on both sides, and they can all cancel out. So what we are left with is g of a plus g of b is equal to g of a plus b. And we also have that g is defined from integers to integers. And from Cauchy's functional equation, the only solution to this is that g of x is equal to cx. And since we define f of x as that, we know that the only solution to f of x is f of x equals cx plus f of 0, which we're going to call d, because why not more variable names, right? Okay, so we have this is the only solution, and we are almost done here. The only thing left would be to plug this back into our original equation to check what specific parameters for c and d we must have, because obviously not all of them would work. We only want these two solutions. So if we plug this back in here, let me actually do that up here, we would get f of 2a is equal to 2ca plus d, and 2f of b is equal to 2cb plus 2d. On the right hand side, we would have, first of all, c of a plus b plus d. We multiply this entire thing by c, and then plus d. So actually, let me erase some of these that we actually don't need. And we can expand that equation, and it should hold for all a, b. So that we would get 2c a plus b plus 3d is equal to c squared a plus b plus c plus 1d. Well, to make sure that it holds for all a and b, we must have these two coefficients be the same. And so 2c equals c squared. In other words, c equals 0 or c equals 2. When c equals 0, we must have these two also be the same, which means 3d equals d. Well, that just means d equals 0. So c equals 0, d equals 0 is a solution, and this would just point to f of x equals 0x plus 0, which is just 0. And that is our first solution there. When c equals 2, well, this is also 3d, so these two are already the same, and these two are the same. So the value of d actually doesn't matter. So we have that f of x is equal to 2x plus d is also another solution, which points back to our original one over there. And there we go. We've proved that these two are indeed the only solutions to our functional equation. So as a quick recap, the first thing we did was we guessed the answer, and then we plugged in some values for a and b as usual, specifically 0, which turned out to be really helpful here. And then we got something like this with vs substitutions. So the key part and the most difficult part of this problem is actually to notice that this looks really similar to Cauchy's functional equation. Then, on that, we would have to, noticing that, we would have to take action on that and use a substitution for g of x to actually utilize our Cauchy's functions condition.